Today, we're peeling back the layers on one of the most fundamental, yet kind of invisible concepts in all of technology, computer architecture. So let's just dive right in. Have you ever really stopped to think about what happens when you tap on an app? You touch a piece of glass and this entire world just springs to life. How in the world does that simple tap, which is really just an idea, turn into a physical action inside a machine? Well, the answer is hiding inside something that looks a lot like this, a microprocessor. You can think of it like an incredibly complex, beautiful little city made of silicon, where all your commands get carried out. But this is the final stop. The real magic is in the journey from your idea all the way to the electrons flowing through these circuits.
To really get that journey, we first have to appreciate a massive, fundamental problem that sits right at the very heart of all computing.
See, on one hand, you've got the world of software, the apps and programs that we see and interact with. But on the other hand, you have the world of raw physics, the fundamental laws that control electrons and silicon. And these two worlds, they speak completely different languages. And here's the kicker. That gap between what we want a computer to do and what it can physically do is just way too big to cross in a single step. This is the whole problem, right? This is the central challenge that computer architects exist to solve.
So, how do you cross this enormous divide? Well, it's with one of the most brilliant and, honestly, elegant ideas in all of engineering.
Instead of trying to make one giant impossible leap, we build a ladder. Each rung on this ladder is a layer of abstraction. It's a genius way of breaking a massive problem down into smaller, much more manageable steps. Each layer only has to talk to the one right above it and the one right below it, translating the language one step at a time.
And that right there brings us to our core definition. Computer architecture is the art and the science of designing this exact ladder, these layers of abstraction. It's all about creating a super efficient pathway from the world of applications all the way down to the world of physics.
Now, while that whole ladder is super important, computer architects have a very special focus. Let's kind of zoom in on their world for a second. The real heart of modern computer architecture lives in these three central layers: the instruction set architecture, the microarchitecture, and the register transfer level. This is the architect's blueprint for the entire machine.
First up, we've got the instruction set architecture, or just ISA for short. The best way to think about this is like it's the official rulebook or the user manual for the processor. It defines the specific set of commands, things like add, store, or load, that the software is allowed to give to the hardware. It's the common language they both agree to speak. Okay, so if the ISA is the list of commands, the microarchitecture is the actual blueprint for how to build a machine that can understand and carry out those commands. It defines the real hardware components, the arithmetic logic units, the registers, and how they're all wired together. And finally, we get down to the register transfer level, or RTL. Now we're getting really detailed. This is like the low-level choreography, describing precisely how data moves between all those hardware structures we just mentioned. It's the moment-by-moment flow of information inside the chip. Okay, I know, that was a whole lot of abstract concepts. So let's make this real. Let's trace a single idea all the way down that ladder we talked about. So let's trace an idea from top to bottom. We start with an application, say an encryption app that uses the AES algorithm. Okay, then you've got the software, which is written in C and compiled for Windows. And now we hit the architecture layer. It's targeting the x86-64 ISA, and it's running on a specific microarchitecture, like Intel's Skylake. From there, the RTL describes the behavior of the circuits, which are actually built using logic gates, and finally, those gates are built from physical devices. In this case, teeny tiny 14-nanometer transistors, all of which are governed by the laws of physics. And just like that, we've traveled from a high-level idea all the way down to silicon. Pretty cool, right? But here's what makes this so fascinating. That ladder, it's not set in stone. Not at all. It's constantly changing, constantly evolving.
Think about it like this. Computer architecture is always getting squeezed between two massive forces. From the top, you have application requirements pushing down, always demanding more features, more speed. And from the bottom, you have technology constraints pushing up, limiting what's physically and efficiently possible to actually build. An architect's job is to innovate right in the middle of that squeeze.
And what happens when you innovate like that for decades? Well, the results are just incredible. We've gone from computers that took up an entire room back in the 1950s to a world where we sell billions of smartphones and tablets every single year. This explosion is a direct result of that constant architectural evolution.
I mean, this new post-PC era we're living in has totally different rules. Architects now have to design for devices that are mobile, right? Smartphones and tablets. And those things have to run on batteries and need constant connectivity with Wi-Fi or 5G. This also drove the rise of massive cloud data centers. We call them warehouse-scale computers that work together with our little pocket devices. It's a whole new set of problems that requires a whole new way of thinking about architecture.
So at the end of the day, computer architecture is this invisible, absolutely essential bridge that makes our entire digital world possible. It's the elegant solution that connects our biggest ideas to the smallest particles of reality. And as our demands just keep getting bigger and faster, it leaves you wondering, right? What amazing thing will the next great architectural bridge make possible?